I'll be talking about exact bulk operators and what happens with bulk locality in ADS3 CFT2, and hopefully providing very general lessons for quantum gravity. So just to recap, there's some ultimate goal, and these 3 lectures are sort of hopefully getting us partway towards sort of addressing this goal of understanding the black hole information paradox. This is a tension between Hawking radiation with a completely smooth horizon and unitarity of the CFT. And we talked in the last lecture about how there are very specific concrete problems that are easy in the sense that we can address them by looking at CFT observables. They're basically they're observables that the gravitational theory gets qualitatively wrong, and in the last talk we saw how in certain cases we can understand what the right answer is in the CFT, and to some extent what the non-perturbative effects are that explain the difference. And so the point of this talk is to begin the sort of harder task of asking questions in ADS in a way that's precise enough that it actually can take into account these sort of non-perturbative effects. So these are just review slides. So the problem we'll actually be trying to address.
I'm really sorry.
No, go ahead. Yeah.
The reason we think these might be non-perturbative, just to tie it to the earlier one, as last time you showed any particular block at least shows a decay, and to the extent that that stabilizing at a lower level was a kind of signature of the information not being lost. You're not seeing it. So you have to sum over all blocks, but does it follow it's a non-perturbative?
Good. So actually what I would have said is so in that case, the blocks just don't solve the problem. The cleanest case was in differentiating a pure black hole microstate from the canonical ensemble, which I actually think is in some ways maybe more relevant and to the actual problem, because I mean you might expect different answers in different microstates. These singularities. So the singularities were, in a very clean way, the singularities were resolved by non-perturbative effects at large central charge, and they were actually seen at the level of the blocks. But I mean, there's a more general philosophical point, though, just to emphasize, which is that if you do perturbation theory order by order in 1/c in the CFT and in G Newton in bulk perturbation theory, you expect that these things should match. And what that means is that since working order by order in perturbation theory in the bulk doesn't solve any of these information paradox type problems, it doesn't explain how the information gets out of the black hole, for example, you wouldn't expect perturbative effects in the CFT to explain what's going on either. So that's the real sort of more fundamental reason why we expect it to be non-perturbative. Another way of saying it for some of the observables we talked about yesterday is that if you really work on this ADS-Schwarzschild geometry, then for example, the fact that a black hole is a thermal state is really built into the geometry by this sort of Euclidean periodicity just of the geometry. And so you wouldn't expect that like loop corrections in gravity can change the geometry qualitatively. It has to be something else. So that's the reason why I use the words non-perturbative.
And I might be just anticipating what
Go ahead. Yeah.
But I didn't get a chance to ask this to you after your last talk.
Good. Yeah.
You know, when Maldacena wrote that paper of his, drawing this analogy between the correlator dying out and it stabilizing, one of the suggestions he made was that there's another solution besides the black hole, which is just ADS with a thermal gas.
Yes.
As you say, a non-perturbatively different background. And at least there, the correlator will stabilize to some value, suggesting the non-perturbative effect. And you didn't talk about that kind of a thing in your last talk, but maybe you'll get to it today.
So I actually won't. So I think that's now viewed as the wrong answer. I think everyone agrees that isn't the explanation. There are a couple. It's sort of wrong in a couple of different ways. So for us, it was wrong in a way that didn't apply for Maldacena. So Maldacena was truly studying an eternal black hole, which meant he was truly studying the canonical ensemble.
Yeah.
What we showed is that at least at the semi-classical level, you can't really tell the difference between a pure microstate of the black hole and the canonical ensemble. So at that level, it's the same answer. What Maldacena was sort of suggesting is that in the canonical ensemble, you get contributions from all sorts of different states, and the vacuum, for example, being one of them, so that this tiny contribution you get to the vacuum perhaps changes what the behavior is at late times. But if you really study a black hole microstate, then it's very unclear what you would mean by doing that, because you're not summing over states, you just have a specific black hole microstate. So it's not like you get a contribution from in any way that we understand, from sort of a solution where the black hole isn't there. The other sense in which it's wrong is that it's true that this contribution from just the vacuum gives you some part of a correlator that isn't decaying at late times, but it's not giving you sort of the full correlator, part of the correlator that's not decaying at late times. So, I mean, I guess the way to make this most clear is that if you just have this vacuum 2-point function, basically Maldacena was sort of pointing out you could get this vacuum 2-point function with a very small coefficient, but the vacuum 2-point function is just something that, say, oscillates periodically with a period set by the ADS scale. The true result at late times has some very complicated chaotic fluctuations that are basically due to all these different exponential phases coming in and out of phase. And the vacuum by itself doesn't capture that. I might capture one part of that, but I mean there's some infinite sum of other things. So I think that idea for what the solution was is not really the whole answer.
Suppose we stick to the canonical ensemble and we're interested just in the question of when the decay cuts off.
Yeah.
Do you think it gets the answer to that question correct?
I think so. I think it probably gets that. Well, I mean, in the sense that the vacuum contribution is some first contribution, and it has a coefficient which is the rough order of magnitude, the sort of right size. So in that sense, if you take the black hole contribution, it decays and gets smaller and smaller and smaller. This part is sort of some finite thing that's contributing. And so once the black hole part that dominates at early times has sort of completely gone away, this last piece is there. I mean, it's not really resolving the information loss problem, though, in the following sense. So what you would really like to say is that since you pinged the initial black hole state with some light probe, and then you're reading out what you got at late times, you should expect that there's some actual signal of what operator you use to ping the black hole. But this vacuum contribution is, I mean, I think it's not really telling you anything about what information was there, like how you changed the state. Because it's going to be the same vacuum contribution no matter what you ping the black hole with.
Well, if you ping the different operators,
you get different 2-point functions for the operators, yeah. But
okay, but you know, the time of decay, the time at which the exponential stops,
yes,
is clearly entropy in units of temperature
yes.
times a number. Do you think it gets that number? I mean, should I take it seriously quantitatively at all? Is there some question to it?
I'm not sure. I'm not sure what the answer is. Yeah.
And sorry, and what is wrong with the other?
What is wrong with?
Let's say we're interested just in the canonical.
Yeah.
So a particular Malthus is different.
Mm-hmm.
I'm interested in the canonical ensemble. Malthus identified some obvious instant terms that do contribute to the canonical ensemble. So you're saying there must be other contributions as well. Is that beyond the realm of semi-classical gravity, or are there new instant terms that we missed? Or, I mean, what do you think?
I mean, I think there's a pretty clear thing that can be said if you sort of think about this in this kind of bootstrap language. I mean, so I didn't draw these channels, and I should have probably last time since we discussed this question so much. So there's some statement where I have, say, the light probe, and I have this heavy thing. So, I mean, some of us very much, I think, had this in mind, but maybe other people weren't. So there's a sum over here, and there's a sum over here of states that are running in so I don't know, there's some state psi in this channel, and there's some overstates psi in this channel that we're considering. So I believe that
And time runs out.
and time, yeah. So this is sort of like time. So when I was sort of talking about cutting the cylinder and inserting a complete set of states, and these are different states that run in these channels. So for example, the vacuum naturally runs in this channel. I mean, I'm not sure that I can literally, well, in the canonical ensemble, there's an additional sum, which is a sum over all of these heavies weighted by a Boltzmann factor. I could put that in if we need to, but let's just think for a second. The semi-classical answer that you get from bulk gravity corresponds to some, well, it corresponds in this channel to summing over sort of the gravity field being exchanged between light and heavy, which very specifically in a bootstrap language means like the stress tensor squared, and all sorts of other multi-trace operators made from the stress tensor. So that's the channel that we've been working with very often, because this is the channel where I've been computing blocks and saying that they know about gravity in ADS3. So in this channel, this is the channel that's supposed to make it obvious that you will never get decay, because the blocks in this channel are some complicated function. Roughly speaking, the blocks in this channel are not complicated functions at all. They really just, all of these blocks just go like e to the I energy t for whatever the nth state is, and there's an infinite sum over all of these states, and they have some coefficients which are products of OP coefficients here. So they have some coefficients lambda n. These lambda n are also all positive coefficients by unitarity. Okay, so.
And then there are the integers from the descendants.
And then there are integers from the descendants. I mean, I can even ignore conformal blocks and just say there's just some sum of discrete states. So I think what so what Maldacena is pointing out is that in the canonical ensemble where you're summing over H, there's a contribution where H is just the identity, and this is just the propagation of the light particle by itself, and that's a contribution that doesn't decay. So that's just from the state, which is the light particle, where H is the heavy thing. Now, that is a contribution in the canonical ensemble that's there. You know that it's going to be suppressed by e to the minus temperature times, well, it's going to be suppressed by roughly e to the minus s black hole, because most of the states that are dominating are very heavy states that are near the mass of this heavy black hole, and so the contribution of this sort of pure identity piece is very, very small. So I mean, that's just what was suggested. Now, in the correct answer, there's an infinite sum over all sorts of different states of different energies, E, and at early times it's very much dominated by the states with energies of order the black hole mass. I don't see any reason, I don't think that these high energy states, they don't all cancel out at very late times. I mean, they also make a contribution just like this does. So I'm not positive, I'm not sure whether it's theory independent or whether it's completely universal, but I mean, the vacuum does make some contribution. It's of order e to the minus s, but I don't know, there's no reason to sort of single it out as special. And most of the states that are contributing here don't have some particularly useful semi-classical. I mean, of course, in a certain sense, you have a distribution of black hole states weighted by a Boltzmann factor. So you could just imagine sort of summing over all black holes that with different masses weighted by a Boltzmann factor. But yeah, I don't know beyond some statement like that whether there's any semi-classical instanton interpretation that's useful. Good. Okay. So that was just recap. Yeah. What we're interested in doing today, so this was a problem that you can address just within the CFT, where you can see that classical gravity gets the wrong answer, and this is a situation where potentially you could try to understand non-primitive effects to give you the right answer. For this question, I told you the punchline was non-primitive effects change the answer significantly, but they don't fix the problem completely. You actually need an infinite sum over blocks. So when I say non-primitive effects, I mean within these Virasoro blocks. You really need to know the whole theory to get the exactly the right answer. For this other problem with forbidden singularities, the blocks just had non-primitive effects that solved the problem. Okay, And so what we're interested in now is how can we study observables in anti-de Sitter space, which are the observables that we would actually care about if we're viewing this as a model of quantum gravity for our universe. They're the observables that, like, if you're in a rocket ship hovering outside a black hole, those are the measurements that you make.
One
Yeah.
quick comment.
Yeah.
You know, we know that in some contexts, gravity reduces to hydrodynamics.
Mm-hmm.
And this kind of jitter is like the jitter of the details of the hydrodynamic state, the details of what the atom will do.
Yeah.
That quantizing gravity is sort of like giving loop effects in hydrodynamics. And you can imagine that that gives you some smoothened out average of this jitter. It clearly can't capture the jitter effect. So I wonder if the instance somehow give you some sort of average of this.
I think that's reasonable, yeah. Yeah.
You're assuming there is an instance other than the thermal gas.
Well, the thermal gas for a certain amount of time might give you the right average. Now at double exponential time, you have to think much harder to try to get that.
Yeah.
So also maybe a related comment is in models like DSYK in which the random fluctuation was smoothed out
Mm-hmm.
after you disorder it, there maybe you can expect, it's more reasonable to expect that there's an instance on that.
Yeah, so yeah, I mean, I don't want to discourage you from looking for instantons in general. Yeah, I don't mean to be particularly discouraging. I mean, there's this specific ADS3 CFT2 context where there's this very precise block decomposition, and that's where I'm saying I don't know what the instantons are. If you have some, I mean, the SYK model is a microscopic model of quantum gravity, and I mean, various people using observables very much like this are trying to figure out, like, can they find all of these timescales? And in fact, the time dependence that comes about from these statistics is much more refined than I'm discussing. I mean, there's all sorts of different features in it that are interesting. So, I mean, there's a lot more to say about this, and I'm just not talking about it.
So just to say, I mean,
Yeah.
in 3 dimensions, you have this, besides the thermal ADS and the DPZ,
Yeah.
you have the entire bunch of SCTZ family of solutions. Can they play any role in here? I mean, you know, you have all this story about, you know, the fairy tale sum and whatnot.
So you have to be careful what observable you're talking about, I think. Here I was talking about a 4-point function. There's an observable that you can study which is basically an analytic continuation of the partition function, which is what people are studying with the SYK model. The advantage of that observable is that you don't have to talk about a light operator and a heavy operator, and it has far fewer details. There you're really studying the partition function, and there those kinds of sums that are sort of associated with, they're just associated with modular invariance in the CFT are something you can study. I think,
Well, just the 2-point, just the thermal 2-point function. 2-point function on the torus. That would also get complicated.
sure, yeah. I mean, the thing that I was going to say is that what you're really probing here, I mean, to say it again, is the fact that in this channel, the spectrum is discrete. Modular invariance by itself doesn't enforce that. So for example, if I take the vacuum character and then I sum over all of its SL2Z images, I mean, that's sort of the kind of fairy tale story, and then various other people have thought about this in more detail. That doesn't give you a CFT with the discrete spectrum. It gives you something very complicated that has some sort of continuum spectrum, which of course is what you'd expect, because just taking the vacuum and imposing modular invariance isn't enough information to give you a specific CFT or anything like that. So, I mean, SL2, enforcing modular invariance in the CFT, in the partition function, is literally the same thing as enforcing crossing symmetry for correlation functions. And similarly here, if you take only the identity block, which is kind of the equivalent in the partition function language of taking only the vacuum character, and then you say sum over all of the SL2Z images of the vacuum, which is something you can do, you get something that looks like a semi-classical gravity correlator, but you don't get, for example, the fact that in this channel the spectrum was discrete. So, what?
Maloney and Whittle.
Exactly, yeah, exactly. Good. Okay, so the kind of questions we want to answer are, is bulk reconstruction, if this is reconstruction of ADS physics, even well-defined? And what are the quantitative limitations of it. So the reason why you ask these questions is that there's all sorts of lore from black hole thermodynamics and also from sort of gauge redundancy and gravity that suggests that there aren't any local observables at all. But of course, we know as observers in a gravitational space-time that to a very good approximation, there should be local observables. So what we'd really like to understand is how well can we approximate local observables, and where do they break down, and do they break down in interesting ways in a quantitative level? Yeah.
Your last comment is very interesting. It sort of makes clear, from your point of view, you have to, in order to see this, the real wave-type behavior, you have to see that the partition function really captures integers.
Yes, exactly.
And that seems so far beyond any semi-classical treatment.
Yes. So that's what people are trying to do with the SYK model. I mean, I think Steve Schenker, for example, and many others are like, what they want to understand is that since the SYK model is some, in principle, well-defined thing, and they can write it in terms of this path integral over this bilinear field, somehow, if you were smart enough, you should be able to do that path integral and see how the path integral knows that there's a discrete spectrum.
Very sorry, I
Yes.
missed this. I mean, why does the spectrum have to be discrete? I mean, it does have to be discrete, but integers you just mean discrete. Right?
He mean, well, yeah, I mean, Go ahead.
Trace e to the power minus beta h. It should be possible to write that as sum over ni e to the power minus beta ei. So the density of states is a bunch of delta functions, not a smooth thing.
And that's
That's
what
sort
it
of
would take for the averages to average out and you to get some.
well, to be fair, I mean, I guess if you had a partition function with a discrete set of states, but the number of states at each level was not given by an integer, that might still have this behavior. So, but you're seeing that it's a delta function. I don't know that you're seeing that the delta functions have integer coefficients, but anyway.
But in some detail, you might be able to see it. If
You might.
probe the details of the statistics, you might see it.
Yes, yeah.
Okay, I'm sorry, but this is for the diagnostic where the 2.4 millimeter of say the light field does not decay.
Right.
Is
Yeah,
it for
yeah.
that?
Does not decay. And then if you want to probe the statistics of what it is after delta.
Yeah.
The fact that it's a sum of delta functions with integers probably determines the statistics, has many
Yeah.
implications for the statistics. So how you ever going to get that for what?
Yeah. And so there's a huge literature from quantum chaos about that statistics problem, and there are many papers specifically addressed at this. So. If you, okay. So anyway, we're interested in this question, how can we do bulk reconstruction? Because we'd eventually like to take whatever well-approximated local bulk fields we have and take them near a black hole and see what happens near the horizon and learn whether or not, in a constructive way, physics of the horizon is smooth, et cetera. I mean, we may run into other problems like state dependence, all sorts of other things, but I mean, for this talk, we're not going to be in black hole backgrounds, and I think our approach is we want to just sort of follow our nose and sort of see what we can learn.
And I'm very sorry.
No, go ahead, yeah.
But by bulk reconstruction, you literally mean from all the data of the CFT, how would you come to any notion?
Exactly. So this reconstruction problem in general would be, given some CFT, is there an exact prescription for defining local field operators that somehow correspond to fields in the dual ADS spacetime? And there are a bunch of things that we would like such a prescription to do, most of which are just sort of according with our perturbative knowledge. So we want to be able to specify where in the bulk the field is located. We want our prescription to agree with bulk perturbation theory, not just in the vacuum, but in any semi-classical background. So if we turn on some heavy sources that say create some black hole background, then we should get gravitational perturbation theory around that background, as well as around the vacuum. And then, of course, the sort of end of this talk will be we want to make quantitative predictions about what the regime of validity of this prescription even is.
Just one last comment.
Yeah.
Atish and Ashok and various people have had this long program that has not come to conclusion, which is a program of trying to, in supersymmetric black holes, compute the partition function exactly enough using a bulk path integral so as to see integers.
Yes.
Using only bulk.
Okay.
They've made a lot of progress, but even though it's not gone all the way.
Yeah.
So it seems like that is connected with what you want. Because there, they will, since from your point of view, getting the integers and the discreteness is totally key. If they understand what sort of bulk effects are able to give them that, then in a controlled setting, then perhaps the same thing will work.
So, I mean, I think that that's very, very nice, and I think that's very interesting. I think that the fact that we've been talking about this problem a lot maybe misconstrues my personal feelings. I don't think this is necessarily the most important thing to do. It's just a thing that is very, very well known because, I mean, it's been studied for a decade and a half at least. And so I wanted to talk about it. I mean, my personal view is that I don't know which non-primitive effects, what details of the CFT are going to be important. I just don't know. But this other question about these forbidden singularities and the periodicity in Euclidean time, I think, is, just as interesting as this. I mean, and for example, at the end of the talk yesterday when we were all kind of exhausted, I made the statement that black hole microstates really don't have this periodicity. That seems to mean that there's some sort of sharp thing going wrong near the Euclidean horizon. Now, that's just the Euclidean horizon. I don't know what it means. But I mean, to me, it suggests that that observable, which actually was resolved with these Virasoro effects, might be a more interesting way. Its success or failure might be more interesting for the bulk than this discreteness. No, I mean, discreteness is also interesting. And I think for many people, I think figuring out the discreteness of the spectrum from the bulk path integral is sort of a holy grail. So I mean, I think that's also extremely interesting. But I'm agnostic about which of these effects or problems is most important. I think they're all interesting. OK, so this is sort of the goal that one might have in mind. And we're going to try to see how this is possible. I think basically all approaches that I'm aware of to this problem in the past have been based on some procedure where one takes a large N CFT and sort of a weakly coupled bulk theory, and you sort of try to figure out what the natural relationship is between the bulk fields and the CFT, which means that you're sort of using the bulk to learn about the bulk. What we're going to be able to do is sort of define what the bulk should be without necessarily using calculations in the bulk to get there. Which I think is important in the sense that we want some exact prescription, not something that relies on the bulk itself. OK, so what we'll show is that we can solve this problem using Virasoro symmetry to get an exact bulk protofield. And it's important that this is a protofield. This is not sort of, say, the full field for a specific CFT. I mean, you have a specific, if you had a specific CFT, there'd be some specific bulk dual with a specific spectrum, and you might try to define like scalar, vector, et cetera, fields in the bulk for that specific theory. What we're going to compute is a protofield, which is everything that's encapsulated together and forced upon us by symmetry. So the real full fields will be some sum of these protofields in a general interacting theory, and I'm not going to talk about what that sum looks like. So Cabot, Lifshitz, and collaborators have a very long series of papers studying this kind of question in perturbation theory in the context of general dimensions without all this Virasoro stuff. And I mean, they have some prescription where they start with some free theory, and then they say, well, if I add an interaction, then the bulk correlators will then become pathological, and I have to add more of these kind of protofields together to get to sort of satisfy causality and other kinds of constraints. So that's the kind of spirit. The big difference is that here in ADS3, we're going to kind of fully incorporate all of the gravitational interactions. So we're not going to incorporate non-gravitational interactions, but all of the gravitational interactions will be sort of put together in this protofield. So this is going to be equivalent, if you don't want to worry about this word, this is equivalent to the best you can do, I think, to defining a free scalar field coupled to gravity. So if you imagined that you had some CFT that was dual to ADS3 gravity plus a free scalar field with some mass, where it's free up except for gravitational interactions, then I think this field is sort of as close as possible to what you would mean by that. And then at the end of the talk, we're going to compute the propagator, just the two-point function in the vacuum of this field. And we're going to see that there's some interesting non-privative gravity effects that indicate the breakdown of bulk locality.
And this will be at large C or finite C?
So the point is, when I say exact, I mean at finite C. So we'll have a finite C expression for this field. So first, let's solve a warm-up problem, which has been solved in various ways by many people. I mean, in some sense, going back to the early days of CFT with Banks, but Cabot and Lifshitz have talked about this, many other people have. And let's just study what would be a free scalar field without gravity. So gravity is just turned off. You can think of this as c equals infinity. Okay, so we're going to work in this Euclidean ADS metric. We're just working in the vacuum. This is just a warm-up. This is without gravity. What we're going to do is we're going to write our scalar field in this possibly unfamiliar way. So this is mimicking something called a boundary operator expansion. What we're doing is we're saying that, so we have this ADS metric. Maybe it's useful to draw a picture. We have this ADS metric, and y is the radial direction. Y equals 0 is the CFT. So we have sort of y equals 0, and sort of this is where ADS3 is. So I'll have pictures in later slides anyway, but we have some field phi of y 0, 0 it's sort of being projected into the bulk, and y equals 0 is the boundary. We're going to expand in our definition for phi. We're going to write it as an expansion in small y with sort of all order powers. And at y equals 0, as y goes to 0, y to the 2h is just y to the delta for this scalar operator. And so this is just giving you the fact that as y goes to 0, as you approach the boundary, phi becomes dual to this CFT operator O.
So L minus 1 is the translation?
L minus 1 is the translation. So it's the raising operator in the conformal algebra. I've already made some assumptions when I write things this way. Well, not assumptions, but I've already sort of solved the problem partly by writing it in this specific way, but it's the right answer.
Taylor expanded the smearing.
If you think in terms of smearing functions, I've Taylor expanded the smearing function. The answer we're going to get agrees with what you get by Taylor expanding the smearing function. So now you can do something very, very simple in general, which is you can just ask that this scalar field transforms as a scalar field in the bulk under conformal symmetries. What that means is that when I act with any of these quantum operators, L minus 1, which is translations, L0 dilatations, and L1, which is special conformal, on this object, on the right side, I can act as a quantum operator using the commutation relations of just the global conformal algebra. But I want that to be the same thing as acting with an ADS isometry dual to that conformal transformation.
This is why you're saying you're working in a fixed background.
We're just in a fixed back. Yeah, this is just non-gravitational. Yeah, this is just using the ADS isometries. And if you demand that these act in that way, then you immediately learn that this is a good expression if this coefficient takes this form, and then this operator is exactly the same thing as what everyone has done since 1998 or whatever. So. I mean, I think this was stated in this way most clearly in the literature by Nakayama and Uguri, but the basic idea.
The configuration automatically has this feature?
Yes.
And you're saying it's the unique solution?
It's the unique solution, yeah.
Just a pedantic point.
Yeah.
So this, the O at 0, that 0 is this, what is called 0, 0.
Yeah, it's just this point, yeah.
Sorry, how can it be used, because you know that HKLM can have different kernels,
Yeah, so,
depending on where you read it from there.
well, so I can move this. So this is actually something that I find deeply confusing. I mean, in a certain, so the HKL kernel, there are different forms for it, but the difference between the two different forms integrates to 0. I mean, it gives you no contribution to any correlator. So I specified a point that I'm expanding this around, right? So I can expand this around any point on, this is all Euclidean, and I can expand it around any point that I like. So that isn't,
It's the fact that it's Euclidean. Yeah, Euclidean.
It's only
Yeah.
in calculation.
Yeah.
yeah. Good. So this is equivalent to something else that one could do. You could discover the formula on the previous slide in a different, perhaps simpler way. So the simplest observable that we can ever talk about in ADS CFT is to have a bulk boundary correlator with one bulk field and one boundary operator. It's well known that this is completely fixed by conformal symmetry, and it takes that form in the coordinate system we're working in. So now you can do something very natural for Euclidean CFT aficionados and bootstrap people, which is you can just ask, well, what happens if I think about this in radial quantization? Maybe I separate z and x very, very, very far, and I draw some big circle around phi, and I say phi somehow acts and makes some sort of state, I want to decompose that state into O and its descendants. And I do that by just expanding this function in y. And the expansion of this function in y just gives you the expansion of the last slide. So I can decompose phi in O and its descendants just because I know this formula. I can view this formula as an inner product between the state created by phi and the state created by O. And that's something I can just do. So the way that this is probably most familiar is if you've ever studied the OPE, something that you take the OP of, say, 2 operators, and you write it in terms of an infinite sum of descendants of a third operator. Then you can compute the correlator of that object on both sides with that same operator, and you get a 3-point function, which is a fixed function, equals a sum of these coefficients, and then you can use that to fix the coefficients. So this is the same procedure. It's actually even simpler here. This is exactly equivalent to what we did on the last slide, but phrased in a different language.
Sorry, I'm sorry, just a quick reminder about your previous slide.
Yeah.
What classical problem, if we were in the smearing thing, could you just work the classical problem? You'd be solving some classical differential equations with what?
I think you're demanding that, that you're smearing O in such a way that phi satisfies the the Klein-Gordon equation with the correct mass in the bulk. So I think that's what gives you the fact that the smearing function.
And so it satisfies the bulk equation, and it has boundary condition that it becomes script rho at the boundary.
Yeah. Yeah.
That's basically.
Yeah. Yeah. So it's possible to derive this also by literally Taylor expanding the smearing function. If you like.
Your phi is k value, right? So
Yes.
So therefore, this h and as well as h bar.
Yeah, sorry. So throughout this entire talk, I'm always going to be talking about scalars. So h bar is equal to h. So you're going to see 2 h's appearing all over the place. And I could have written that as delta instead. But,
And in classical problem, the non-normalizable modes are turned off. Euclidean space?
in,
That's the boundary condition.
yeah.
Non-normalizable modes are turned off. That's confusing me. I thought the unique solution was the non-normalizable modes turned off to 0.
It's turned off in the sense it becomes curly, at least my understanding, becomes curly operator O on the boundary.
I thought the normalizable part will become curly operator.
So this is a confusing thing that also depends on whether you're in Euclidean and Lorentzian.
Yeah, in Lorentzian it's fine, but Euclidean I can't understand.
So I believe that there's a formula in Euclidean which is just an integral over, so there's a circle, which, I mean, it would be some circle in the boundary, which if this is the distance y, I think there's an integral over a circle of radius y times a smearing function, which gives you,
I'm sorry to interrupt, but is this not the same problem as solving the wave equation in the bulk with specific boundary conditions at the boundary, meaning the normalizable part of the boundary, and then just reading off what phi is at a particular point in the equation?
no, I mean, well, the smearing function language, I would say, I define phi as an integral of O over this region times some function. So that's not the same thing as sourcing and
No, not sourcing.
Yeah.
I thought you were going to find a solution in the bulk. You read off your bulk field from the solution in the bulk, such that the solution was subject to certain boundary. And the boundary condition I thought was that the normalizable part was what you're going to call.
But I'm confused what you mean, because I want to define a CFT operator, which is phi. So I have to take a CFT operator and do something to it. And I think what the smearing function is it's so maybe you're defining what the kernel is supposed to be. But I'm just saying that phi is equal to the integral over some region on the boundary of some kernel that depends on the bulk point and x of O of x. Yeah.
I'm trying to give you a prescription for finding that. But we talk it.
Okay. Yeah.
Do we have to make it room for
Then we
Okay.
just say that there is no procedure.
Yeah. So I told you we could go for 3 hours. So so this, I mean, this k definitely has to satisfy the wave equation.
Yeah.
Now there are 2 solutions. This may be the sort of shadow solution for k, but I mean. I mean, there is some solution k which is equivalent to this procedure. I don't remember. I mean,
And we have restated the boundary condition wrongly, perhaps that's what's the.
Yeah, this is what.
I'm
Maybe
sorry.
I will know the answer to this.
I think this K definitely satisfies the homogeneous equation, so this doesn't have a non-normalizable mode.
It doesn't have a non-normalizable mode, and this one way of getting a field in the bulk that will satisfy the bulk equation is just solve the equation in the bulk. Right?
sure.
If we just treat the normalizable part of that solution
Yeah.
as the operator,
Mhm.
then that gives us bulk field in terms of operator.
Yeah.
I thought at least in Minkowski space this was the standard thing to do. Is it right?
I don't.
I think it is.
I think this is similar when you just strip off, there might be the normalizable fall off might have some right, which is some power.
I am agreeing
They
with
sort of
that.
account for it so that roughly on the boundary it becomes the
So
same.
what confuses me is in Euclidean space, there is no such solution.
So you have to analytically continue the k. So this k depends in some funny way on, naively I think I could be even getting this wrong, but naively you would say that k depends on something like y squared plus zz bar. And I think you have to analytically continue so that this becomes like a minus sign in this
Some funny
function.
stuff.
There's some sort of funny thing that you have to do maybe with some analytic
It's
continue.
totally clear.
Yeah.
There's a solution.
Yeah. You do some sort of funny, but at the end of the day, there exists a function such that you can do this, which formally in a power series expansion is the same.
Global area, it's not just factual.
What about everyone?
What confuses me is that it seems to me to contradict the theorem that if you have del square phi is equal to 0 and phi is equal to 0 on the boundary, then phi is equal to 0, which is a true thing.
Okay. I see. You're just confused because where is the source if that's
Yeah.
But I think phi is not equal to 0 on the boundary. That's what is happening.
No, but the expectation value of the operator.
Sorry, but the expectation value of phi is 0. The expectation value of phi is 0.
No.
Because you need a 2-point function for it to not be 0.
We should continue later. But
Okay.
what I'm saying is that there are two things you could reasonably interpret as the operator.
Mm-hmm.
Namely, either the normalizable part or the non-normalizable part. But it's clearly the normalizable part.
Yes, it's clearly the normalizable part. Yeah.
So that means you're setting the non-normalizable part to 0.
Which is, I think, physically what you want to do.
And then if you do that, there's a theorem which tells you the only solution is 0. Right? So
I'm not doing classical physics here.
no, but
I think this is a class. What I'm doing is defining an operator. I have to include some. So I think what you're talking about is there. It really is true that the expectation value of phi is 0, but the expectation value of say phi with some other o somewhere else isn't 0, and this is the thing that has the source because I now have to take the expectation value of o with the integral of this times o, and then
let me state my contradiction. I'm really sorry. Let me
Okay.
state my contradiction.
Okay.
If you can produce such a field from it,
Mm-hmm.
then it's a field that obeys the equations, linearized equations of motion in the bulk,
Mm-hmm.
has the property that has no non-normalizable part. But such a field is not.
I don't know what a non-normalized. Sorry, this is some operator valued thing. So
We should go with
Yeah.
the usual kernel, one way or another in Euclidean space satisfies the boundary conditions, it satisfies the bulk equation, it vanishes deep in the interior,
And it turns out to non-normalizable.
and it turns on a non-normalizable source, which then comes with a normalizable component. Okay?
That's true.
I think this is without doubt,
Okay.
right? So at least my interpretation was that here the boundary condition being turned on is such that it is determined when you wrote that expression, is determined if I take y going to 0, which I think is the boundary.
yeah. Yep.
Then I thought you're left with curly O.
You're left with curly o times y to the 2h, which is 0.
Y
Yeah.
to the 2h, which is the leading behavior.
It's the leading behavior.
So
Yeah.
my interpretation was that that is the non-normalizable.
Sorry, but what Shiraz is saying is the non-normalizable part really is y to the d.
Zero.
I think this is the non-normalizable.
Some stripping off might be happening here. That part I'm not sure.
I think this is the normalizable part and this is the non-normalizable part.
Let's.
Okay.
Up to some stripping, it's got to be that a non-normalizable boundary condition is turned on.
But that's not what is done in that's not what HKLM do. That's not my understanding of what they do. At least in Minkowski.
But they work in Minkowski
Yeah,
space.
Yeah.
So then you're saying here when you do it, fine.
Okay.
In Minkowski, I
What you're
agree.
doing effectively is working in a patch and agreeing to turn on a non-normalizable part outside the patch.
Maybe.
Well,
Well, you mean if you take y to infinity, then I don't know.
maybe
Okay.
so.
Okay. Okay. Anyway, so there are these. So the point that I was making is there are these two ways of defining this field. Neither of them uses a smearing function. There's this way, and it gives you a unique answer. There is this way. It also gives you the same answer, etc. And this is an expansion. So since we're talking a lot about HKLL, phi here is being written as a sum of completely dead local operators in the CFT, but it's an infinite sum of those local operators, so it can be non-local. But I mean, if you truncated the sum at any finite order, it would just be a local operator. Okay. Okay, so the lessons of this, from just this warm-up, are that there are two ways we can determine phi. One is we can use symmetries to just directly, algebraically determine the bulk field. That's what we did in the first slide. Or if we know the bulk boundary correlators, we can determine phi by using some sort of radial quantization, where we just expand phi in all of the states that the correlator is defining for us. So I mean, on the previous slide, I mean, we're expanding phi in O and all of its conformal descendants. If we knew the correlator phi with a whole host of other operators, then we could compute the inner product of phi with all of those other operators, and that would define phi as a CFT operator as well via the same procedure. And as I said, we've defined a protofield. You would expect that full capital phis are some linear combination of these protofields with some coefficients in a theory that has interactions besides gravity, but I'm not going to talk about this anymore. Yeah?
The protofield was defined as a sum over L1 to N L1.
Exactly. This is the protofield in the C equals infinity limit, the global limit. That's what the protofield is. This is what you get also, I very much believe, from HKLL applied to just at the level of a free field.
That O0 is the expectation boundary in the CFT, right?
So,
Yeah, that O0.
O0 is not an expectation value. It is a quantum operator.
Yeah, that's okay, on the boundary, right?
In the CFT, yeah. Oh, yeah. O for this kind of script O will always be a CFT operator. It's a CFT primary, and this is just it evaluated.
Then the, okay, go to the next.
Yeah.
Next one. Then actually, your first statement and the second statement, okay, is there's this two version of ADS-CFT that, for let's say, time-dependent geometries, okay, people use this extrapolate dictionary way, banks and.
Yeah.
So it's rather, okay, this two statement, okay, is rather a comparison between this extrapolate dictionary and this within partition function in dictionary.
I guess I would have said, I mean, personally, I prefer I think in terms of the extrapolate dictionary. I mean, I would have said that, I mean, both dictionaries should apply for this, but I mean, in both cases, I'm really just defining a bulk field in terms of a boundary operator, and there's no non-normal, yeah.
They're same, okay, in the free theory they're same.
Okay. Yeah, I mean, I think both of these methods are independent of what kind of dictionary you try to use to define ADS-CFT. I mean, I think that's all I would say. Okay, so now we're going to generalize this to the case of ADS-3 gravity. So we have the same slide that we know a lot about gravity using Virasoro. We've been through this. So we want to use Virasoro symmetry to sort of encode all of the all gravitational effects in phi. Okay, so how do we use Virasoro? Well, in ADS-3, Virasoro only acts as an asymptotic symmetry. As Brown and Hino showed a very long time ago, we can take diffeomorphisms that fall off but not too fast at infinity in ADS-3, and they form the Virasoro group of symmetries. But if we can change the diffeomorphisms as much as we want deep in the bulk of ADS without changing what Virasoro transformation they act as, which means that how Virasoro symmetries act in the bulk is just fundamentally an ambiguous statement. We don't know what it is. However, it's not ambiguous if we, so it only defines an equivalence class of diffeomorphisms asymptotically. However, if we fix a coordinate system, or in other words, if we fix a gauge for the gravitational field, then we can fix what these diffeomorphisms are, not just near the boundary, but everywhere in the bulk, by demanding that they asymptote in the right way and that they preserve our gauge choice. So that's the idea. So we're going to take a specific gauge choice or coordinate system for all vacuum metrics in ADS-3. If it's not a vacuum metric, if there's sort of a gas of particles, then we can't write the metric like this at all, and then I'm just not saying anything. But for any vacuum metric, this is something that we can do. And so this is the gauge choice that we're going to make.
Vacuum solves the vacuum equation.
Solves the vacuum equations of motion for
Solves
gravity.
The
Classical vacuum
There's
equation.
quantum vacuum equations of motion.
Yeah. Yeah, that's the
Where the geometry is ADS3.
yeah. So the geometry is locally just ADS3 in this parameterization. I think these are sometimes called Bonados metrics. So if we choose this, then the asymptotic symmetries are fixed to be the diffeomorphisms that preserve this gauge, and that means that we can actually just figure out what they are. So why do we want to do that? Well, in our warm-up example, we just had the global conformal symmetries are just isometries of ADS. With Virasoro, we will not have isometries. We have more general diffeomorphisms. But the definition of a scalar field is that under a diffeomorphism, a scalar field should transform in a certain way. So I mean, under some diffeomorphism in general, scalar field should transform in this way, where we have some small infinitesimal change in y, z, and z bar, and that's the rule. And so what we'd like to do is figure out what these Virasoro transformations are in our gauge and demand that the scalar field transform in that way. So we worked out what they are. There's this formula. The important feature of this formula, the only thing to note, is that in the limit that z goes to 0, all of the Virasoro transformations with m bigger than or equal to 2 vanish. So you can just see this because there's a z to the minus 1, z to the minus 1, z to the m. So roughly what this means is that, I mean, in this picture that I drew, these Virasoro transformations with m bigger than or equal to 2 don't really move this line at all. Okay. Yeah, of course.
What were those formulas?
So these formulas are
How points in space move on it.
how points in space move infinitesimally under the diffeomorphism, the infinitesimal diffeomorphism corresponding to a Virasoro generator Ln.
But these sort of defined to be these, or these were obtained from some other?
These are obtained from a calculation. So, well, there's a very useful calculation by Matt Roberts where he happened to sort of figure out a general nonlinear parameterization of Virasoro transformations from the vacuum to and among metrics of this form. So, I mean, we used that. That was significantly influential. But basically, what you would do is you take sort of what the diffeomorphisms are supposed to be from, say, Brown and Hanot, and you'd try to fix them throughout the bulk based on the fact that they preserve this form for the metric. So they take S to some S prime. And that gives you some set of equations you can solve. And if you solve those equations, you get this. So there's some algorithm. Yeah.
It is also related to the fact that if you just started with the first term in your previous transparency,
Mhm.
the standard way to write ADS3.
Okay, yeah.
When you did one of these diffeomorphisms and you figured out what S bar would be,
Yeah.
these would be asymptotic isometries. That is, S and S bar would vanish, right?
Yeah.
And that is in accordance with the fact that you're
Exactly, yeah. So yeah, the L0, L1, and L minus 1 just vanish because they're asymptotic isometries.
And others found this as solutions from the Johnson-Mills formulation that, they relatively.
Uh-huh.
And then Novus showed by his transformation that you start from ADS and get to this another symmetry by diffeomorphism, which is a finite version of transfer.
Sorry, and phi bulk due to an operator of what dimension?
Good. So that will come up on, I think, very soon.
But should
These
for the action of LM on phi, should that matter?
no, it doesn't. So I mean, if we go back to the these don't. So you can ask. So I mean, you're making the point that when the transformations act on a CFT operator, there's a point, say L0 acting on a CFT operator is something like ZDZ plus H.
Delta.
Yeah. So the way that arises actually from the dictionary is that this is how L0 acts on phi. I mean, this is just some basic ADS CFT fact. But in the limit that we take y to 0, I mean, you act with this on phi. Yeah, and so this term becomes the, yeah.
Thank you.
Yep. Okay, so these are our transformations. they have this very nice property that they vanish as z goes to 0 for m bigger than or equal to 2. This is just an observation. So what that means is that we can write down a bunch of equations for phi. I mean, we want phi to transform correctly under all of these transformations. But there's something very nice and simple, which is that all of the Lm bigger than or equal to 2 preserve the point y, 0, 0, not just at the origin, but along this line into the bulk. So that means there's some very simple algebraic condition which says that these LMs, when they act on y, 0, 0, should annihilate them.
Wait, did you tell us what your gauge condition was?
Our gauge condition is just preserving this metric.
And can you say some words about it? What it's like that?
I mean, it's sort of like Pfefferman-Graham. It's Pfefferman-Graham, yeah. Good. So, so in that gauge, Virasoro acts in this way, which means that our bulk field as a quantum operator should satisfy these conditions, that it's annihilated by all Lm bigger than or equal to 2. It's not annihilated by L1, so I mean, if you know things about Virasoro, this is very funny. It's sort of like phi as a primary, except it's not a quasi-primary, because it's not annihilated by L1. So we're going to we're going to use the same boundary operator expansion we had before, except now these script L's are arbitrary polynomials of Virasoro generators at level n. And so now we just take this decomposition, we demand this equation, and then we need one more condition, and that one more condition, most physically, is the statement that in the limit that c equals infinity, we just get back the global expansion. So we need these equations have, I guess, I mean, they have a unique solution up to some normalization, and then that normalization is fixed by the fact that at c equals infinity, we get back the global field. And so this equation, the statement that at c equals infinity, we get the global field, plus these, has a unique solution. And that solution defines all of these script L's and coefficients, and that's how we define our bulk field for any value of the central charge.
So the lambdas are the same.
Yeah. So I mean, the lambdas. I mean, you could absorb them. So we chose the lambdas to be the same for global and Virasoro, and then everything else is in these ln's. So here's an example. I mean, just to show you that this is exact in C and H. This is L minus 2. This is just the solution. It takes this form.
Sorry, can you just go back to
Yeah.
What is I didn't fully understand, what was the difference between phi and phi global? What's the difference with script ln and?
Good. So phi global doesn't satisfy this condition. For example, if I take L2 and act on phi global, then like L2 when it acts on, say, the level 2 part, that'll be like L minus 1 squared, and L2 acting on L minus 1 squared is some finite number. So at level 2, you have to take a linear combination of L minus 1 squared and L minus 2 so that it's annihilated by L2. It'll automatically be annihilated by L3 and all of the higher ones just by level. So I mean, that's how one solves. And so that suggests, I mean, at level 2, there's just some simple algebraic equation you solve, and that's the answer.
But, sorry, if you can just go back.
Sure.
So then what is the relation between lambda? So what's the additional boundary condition that your phi satisfies that relates it to phi global?
Oh, so I mean,
So phi satisfies the equation you mentioned, that Lm acting on it vanishes.
the Lm acting on it for m bigger than or equal to 2 vanishes. And then what I was saying is that just saying that L2 annihilates phi, say at level 2, fixes the linear combination of L minus 1 squared and L minus 2. But then there's some normalization of that object. And I'm fixing that normalization by demanding that in the limit c goes to infinity, I get back a globally reconstructed bulk field.
So it's basically that all the correction terms come with a 1 by c.
Yeah. So if you take this formula and you expand it,
Throw in the terms of the c.
exactly. So you can see the L minus 2 part has a 1 over c in it, so it goes away, and this is
Thank you.
great. So this is just an example. And so the point of this equation is just to say that this is really an exact function of C and H. And so that means that we can be sensitive to non-perturbative effects in gravity.
The normal family of phi would be generated by taking off this phi by L1 on this L1 L0
Well, Well, so what I would say is phi is in the same conformal family as O. I mean, phi is really just a linear combination of O and its descendants. It's an infinite linear combination labeled, parameterized by this variable y. So I mean, like, in principle, like from phi, you could act with some very complicated operator and get back O, or you could just take y to 0 and get back O, and then you can sort of build back the conformal family.
But if I were to just take these conditions, right?
Yes.
And L bar m, they give phi for m greater than equal to, so a priori I can act with L1 and L0.
Yeah. So if you act with L1 on phi, then it isn't 0. Yeah, it acts non-trivially on phi. I think it acts as some special conformal transformation.
I mean, the conflict seems to be clear because here we are conform family constructed by acting also with L1 along with L1, along with other relationships. Why for O we just act with standard, there's a standard conformal.
I think I don't understand. So O is exactly a primary. It's annihilated by Lm for all positive m. This object shares the feature of O that it's annihilated by all of these with m bigger than or equal to 2, but it's not annihilated by L1. As you can see, in fact, no power of L1 will annihilate phi. No finite power of L1 will annihilate phi. So I mean, phi is it's just an infinite linear combination of O and its Virasoro descendants. I mean, you can act on phi with any of the
If I
L's.
don't look at the expansion of phi,
Yes.
I would just look at those conditions.
Yes.
If phi is so big.
Yes.
And now I construct the representation, highest representation from the acting with L1 onwards.
Oh, you can't. If you act with L1 any finite number of times, you never get 0.
I don't want to get 0, I want to construct this modulus.
Okay.
That's how we construct modulus, right? By using operators that don't kill it.
Good. Yeah. I mean, L-1 and L1 both don't kill it.
Okay.
Yeah. So I mean, maybe the confusion is phi isn't really a local operator. So if I truncate this at any finite n, then I would get a sum of local operators, and then I could, for example, act with L1. If I truncate at some capital N, then I could act with L1 to the n, and I would get back phi, and then I could build back up the module. But here, this is some non-local thing, so I'm not sure sort of what happens. Okay, but yeah, we can talk about it more.
So where here have you used that you're doing the active equation before?
That's going to be the next slide. Good. So now, this is all some algebraic construction, but how do we know that it has anything to do with reality? By reality, I mean, say, bulk gravitational perturbation theory.
This expansion that you obtained
Mhm.
using these conditions, could you also have done it using some sort of a correlation that you did for the global block?
That's exactly what we're about to do. Exactly. So both of these questions are closely connected. So as we said at the beginning, you can define, and you're just pointing out, we could also have defined phi by knowing all correlators of this form, and then decomposing phi into O and its descendants. So in the global case, all we needed to know was the correlator of phi with O. But here, we need to know the correlator phi with all of the Virasoro descendants of O. What that means is we need to equivalently know the correlator phi with O in any number of stress tensors and anti-holomorphic stress tensors. If we knew this, then we could just decompose. So how can we compute these correlation functions? Well, we have a prescription for that. And the idea pictured here, so this came out of some work we did about a year ago. So I mean, a general question you can ask about any CFT, and in particular 2D CFTs, is you can ask for this thing called the OPE block that was defined in a nice paper by Czech, Sam McCandlish, and a couple of, I'm not going to be able to, I apologize, I'm not going to remember. But anyway, there is a notion of an OPE block, which is all of the terms that enter in the OPE of two operators as an operator-valued object. And something that we found about a year ago is that for the Virasoro, for Virasoro symmetry, you can compute the OPE block of two CFT operators using Chern-Simons-Wilson lines. There's some exact Chern-Simons-Wilson line prescription. This also allows you to compute Virasoro conformal blocks, because once you know the OP block, you can take the inner product of two of them, et cetera. And so this is some nice thing. So now, a natural thing one could do is compute the OPE block. So if O and if phi was another O, this would just be this Chern-Simons-Wilson line prescription. A thing that you can do that's natural is you can ask, what happens if I just move one of the endpoints of those Chern-Simons-Wilson lines into the bulk? Now, an even simpler thing you can do, which is even more straightforward, is actually equivalent to that, but without anything fancy involving Chern-Simons, is you can ask, what if I compute a first quantized path integral for a particle propagating from O into the bulk to the bulk point phi? And so I'm moving in some general bulk metric, and I interpret the bulk metric as a dynamical gravitational field. So in other words, I'm doing something that's probably very familiar from studying either Wilson lines or just particle propagation in, say, QED. I mean, if I have some first quantized trajectory of a particle that has a charge, then there's some integral along that particle's trajectory of the gauge field dotted into its trajectory. And if I'm perfectly free to view that gauge field as some quantum gauge field, and then I can compute things like the radiation properties of that object. Here, I'm doing the same thing, except I'm using the gravitational field. And in our gauge, the sort of quantum gravity field is just given in this form. It's the same form as the metric we had before, but now we interpret T as the actual quantum stress tensor of the CFT. So this prescription is equivalent to this Chern-Simons prescription we used previously. But there's this one extra thing that we're doing here, which is we're taking phi to be a point in the bulk. So instead of drawing sort of a trajectory from one point in the CFT to another, which might go through the bulk but ends at the CFT, I'm just going to push phi into the bulk. And what this does is, so I've drawn this circle around O and phi. The idea here is that this is defining an OPE block for O and phi. In other words, it's defining the sum of O and all of the operators in the sort of OPE of O and phi that are in the Virasoro sector, that, in other words, consist of many, many gravitons. So this is nice because now I can use this to compute the correlator of phi and O with any number of stress tensors, because I have, what this turns into is this is some line integral of the stress tensor, and then there's just a bunch of extra stress tensors around. I know all stress tensors correlation functions, so I can just do this and compute an answer. And I should say one caveat to emphasize that there is a caveat here. In general, these line integrals won't be convergent. For example, if I have many stress tensors on this line, then they have some OPEs, and so I have to worry about there being some divergence. So I have to regulate this object to make sure that it's well defined. There is a, I think it's unique regulator that when O and phi are actually just two CFT operators, in other words, I took y to 0 and phi just goes to the boundary. When O and phi are two CFT operators, there's a unique regulator that gives you the correct answer. The reason you know what the correct answer is you know the correlator of two CFT operators with any number of stress tensors. That's just completely fixed by Virasoro ward identities, so you know the right answer. And there's a unique choice of regulator that agrees with that answer. Now, once you define that, it's very natural to say, I'm going to use that same regulator, whether phi is on the boundary or moved slightly into the bulk, and that's what we did. Now, I mean, maybe you could say this even more strongly, because not only do you know what the correlator of O is with any number of stress tensors, but if I take descendants of O and I compute their correlators with stress tensors, I also know those. And so in an expansion in small y, I think you really sort of know this answer, but there's some maybe extra statement that we're pushing it into the bulk. Good. Yeah.
Okay, so if you were on the boundary, of course, as you say, you wanted to take the endpoint correlator of two operators, O, say, with any number of stress tensors, that's
Yes.
totally fixed.
Totally fixed, yes.
But now what you're doing is you're interested in computing such a quantity where phi is in the bulk.
Is moving into the bulk,
Is
yeah.
moving into the bulk,
Yes.
right? Okay, so that I get. But then what was this OP block that you're using for this process?
So you can ignore the words OP block if they don't really matter.
Okay.
The only reason why I said it that way is that this line integral here is a sort of, it's a line integral in this exponent, there's some line integral of the stress tensor, and that object gives rise to the correct linear combination of Virasoro descendants that correspond to sort of the vacuum and its Virasoro descendants in the OPE as sort of like phi and O are being OPE'd. But I mean, you can just ignore that language and just say, I'm computing the natural line integral for a particle to propagate from O on the boundary to phi in the bulk in a quantum gravitational field, and I'm just sort of expanding it.
So what I'm missing is, I thought up till the last transparency,
Yes.
that you had now defined phi of y0 through your curly L's.
Good.
You knew what the curly L's were, and you were going to use that now.
Good. So
And now there's a jump.
there's this jump.
Which
Good.
I don't quite get.
Oh, good. So in the warm-up, we had two different ways of determining phi. One was by symmetry, and one was by knowing the correlators. As Abhijit asked, we can say, well, is there a way of doing it using correlators? What I'm presenting to you is a totally independent way of defining phi, which is equivalent, which will turn out to be equivalent to the curly L thing that we started with. The reason why I'm even, so you might say, why do I even tell you about this? The reason I'm telling you about this is that this has an extremely nice feature once we know that it's true, which is, say we turn on a bunch of heavy operators all over the place that give the stress energy tensor a VEV. Then we get a bulk metric, which is not just sort of trivial vacuum ADS, but is of our gauge fixed form. What this fact, the fact that our correlators can be computed in this way, guarantees for us is that our prescription will give us the correct two-point function for O with phi in any semi-classical background that takes this form.
What I didn't understand is why your first method also did work more generally than for vacuums that were just doing.
It does. Sorry. So both of these methods are exact. They give you the same quantum operator phi.
But you seem to be saying that the first method in logic did not work only in.
No. So if we could have just done the first method and been done, and then just said we're very happy. This is what you can think of as this is a check that the first method makes sense, and I think it's a much more explicit way of understanding why it gives you the right answer. But you're right. I mean, you should have expected from the first method that this property would hold, but this allows you to check it in with a bunch of calculations. So in other words, you can use this procedure. You can compute the correlator of phi O with any number of t's, and you can just check that that's the same as the correlator of phi O in any number of t's using the definition with the curly L's from the earlier slides.
Sorry, I didn't quite understand this, but
Good.
the fact that you're using a first quantized description here with a mass, does this work for any operator of any dimension, or only when the dimension is much bigger than unity, so that it's a very heavy?
So I mean, formally this. So the formal answer is it works for any operator with any dimension. I mean, seeing why that is might be some technical thing, but yeah, this works for any operator.
He's doing the path integral. He's not just doing the classical.
Yeah. So I'm doing this path integral over all trajectories between z and y that do this.
Like solving a way.
It's all, yeah. So it turns out that there's a technical simplification where that path integral takes a form that can be rewritten in terms of just a line integral, but formally you're defining this using this path integral over all trajectories.
I see, okay, sorry. And the mass corresponds to the anomaly.
Yeah, it corresponds to the dimension of O. Exactly. Great. So, yeah. Okay. Yeah, so, I mean, it was guaranteed, it should have been guaranteed that we would have the correct correlators in any vacuum geometry from our original definition, but this allows you to check this in a lot of detail and be persuaded that you're not doing something wrong. And so, as an example, the first non-trivial correlator you can compute is the correlator phi O with a t, and this is the form it takes. A fact is that, so I mean, maybe a point that I should tell you and emphasize is that this, at least if you know a lot about 2D CFTs, there's a singularity as a function of the position of the stress tensor Z1 at the position of O, so that's this singularity. And that's what you would expect because the stress tensor has to be able to measure the energy of O. There's also a singularity at location Z1 equals 0, which is the projection of this operator back onto back into the CFT plane. And that you can think of as due to the fact that in our gauge, there's some sort of gravitational Wilson line running directly perpendicularly back from phi to the boundary. And that's how T knows about the energy, momentum, et cetera, in this bulk field. Yes. So in fact, that's how we first discovered the symmetry argument. The fact that it's Z1 cubed, so a thing that you might know if you know a lot about Virasoro is that you can extract the action of Virasoro symmetry generators on some operator by doing a contra integral of the correlator of T with that operator. So what that really means is that when T has a certain singularity with phi, that means that certain Virasoro modes act on phi. So the fact that this is Z1 cubed but not a higher power is what tells you that L1 acts on phi, but L2 and higher actually annihilate phi. So in fact, we first computed this, and then we observed this fact, and then we realized there should be a symmetry. So that's the state. OK. So that's how we defined the operator phi.
And it's particularly important for you that it works for BTZ black hole because you want to probe the horizon.
Exactly, yeah. And that's true because the BTZ black hole is a vacuum geometry, I mean, until you get to the singularity or something. Good. So, but we're not going to probe BTZ black holes in this talk. We haven't done that yet. We're just going to compute the vacuum propagator of phi. So now we're going to study the simplest thing, phi of x, phi of y. A point that I'll make is that this correlator should be real. I mean, we're actually only going to compute this at space-like separation, so it should really be real by unitarity. The phi quanta can't decay. And because it has this simple definition in terms of Virasoro, we can adapt a lot of the techniques that we use to compute Virasoro blocks to also compute correlators of phi. So that's what we're going to do. So just to define some kinematics, for phi of x, phi of y, I'm always going to use the variable sigma to denote the geodesic distance in vacuum ADS between x and y. And we're going to often expand this in terms of this variable rho, which is e to the minus 2 sigma. So in other words, rho is 0 when they're very, very, very far apart, and rho is 1 when they are at the same point in the bulk. A point that may or may not surprise you is that our gauge choice differentiated between the ZZ bar plane and the y direction.
Sorry,
Go ahead.
Earlier in the global case,
Yes.
Your phi was some smearing of the optical on the bound.
Yes.
Presumably that's still the case here.
Well,
O and T, maybe.
yeah, I mean, you can think of it that way, but we don't know of a formula that writes that nicely.
In the case where gravity was not allowed to be there.
Yeah. So we don't know if there would be any nice form for the smearing function. Good. So this is just kinematics. Sigma is a geodesic distance. This point is kind of interesting, though. So our gauge choice made the ZZ bar plane different from the y direction. What that means is that you might not expect that the correlator will only depend on the geodesic distance between these 2 points. It can also depend on an angle of, say, the sort of line between the 2 points with respect to the ZZ bar plane. So in general, this correlator is not going to be sort of spherically symmetric. So in principle, it can depend on the angle with respect to the radial direction. For simplicity and practicality, I'm only going to sort of tell you, effectively, I'm only going to tell you about results when the 2 phis are in the ZZ bar plane. So that's the limitation of what will happen. So since we're going to work in the ZZ bar plane, we're going to write everything in terms of rho and the geodesic distance.
Just a general question.
Yeah.
In the global case, which presumably is HKLL,
Yes.
there, though you can word it all in some fancy quantum mechanical language, every calculation is essentially a classical calculation.
Yeah.
Kernels are computed by solving some classical data.
Mm-hmm.
Are you going, because you're not working at C equals infinity,
Yeah.
somehow going beyond that?
I mean,
Everything you're doing by solving classical differential equations in ADL.
I really don't think so, but
You think not?
I think not. I mean, we're going to have pure 1 over C corrections that don't care about,
At some point, yeah, I got a bit confused because while we were discussing the pure ADS case, even though we were defining a bulk operator,
Yes.
Now, once we allow fluctuation,
Yes.
what does the local bulk operator mean? And you're somehow defining a local bulk.
I'm defining a local bulk
So
operator.
What does that mean anymore?
So what it means is that this has all of the properties that one would ask, I think, of a operator that you would call phi of y z z bar, where the position of the operator in the bulk is defined to be where it is in this coordinate system, right? Because I mean, we fixed a gauge, so that's how we're specifying where the operator even is, right? Is that by the coordinate y and z bar in this gauge, and that's so this is supposed to have all of the properties that would have, and I mean.
Right, but I understand, but now we are allowing for the metric not to just be ADS.
Yes. Although the metric, the only way, I mean, the metric can't just take whatever form it wants. The metric can only take the form that it would take in response to some heavy source or something like that. So, I mean, if you want to make the metric non-ADS, you have to say, put a heavy operator somewhere and have T of Z be sourced, and then you should get the right answer in that.
Plus the diffeomorph, the large diffeomorph, in addition to these sources.
Yeah. Yeah, so I mean, you could study a state that isn't the vacuum, but is a large Virasoro transformation of the vacuum, and then
Automatically taken
that should automatically be accounted for as well.
Yeah, so this is, I mean,
So, I mean, what does it mean anymore? So, okay, you allow your, if you start with your diffeomorphisms, already, of course, the physical point changes in terms of what its Y values are,
Mm-hmm.
and so on. Then in addition, you allow yourself heavy sources. So, in what sense is phi at some point Y a physical operator?
Well, I mean, here's a clear statement that I think is just very caveman-esque, as one of my friends likes to say. I mean, the 2-point function of phi to all orders in 1 over c will be exactly equal to the 2-point function you would get by studying a free scalar field coupled to gravity and just computing loops. So you can compute the 2-point function at 1 loop, 2 loop, 3 loops, et cetera. And I mean, I think that's a very natural thing you can do in the bulk. You can fix a gauge and then just do the gravity loop expansion. I mean, we'll have a diagram, I think, on a slide or two that just, well, I mean, probably it's like, we'll compute things like this diagram, and that diagram will agree with, I mean, the result of just computing that diagram like a naive person will agree with the 1 over c correction to the 2-point function.
Okay. So you should say, but perhaps what you're saying is defining the location vis-a-vis the c going to infinity metric, and then do perturbation theory about it, but continue to use that metric as a to define what.
Well, so that agrees with our proposal to all orders in 1 over c, but since phi is defined exactly, we also can just tell you what the exact answer is supposed to be.
yeah, I think I was going to ask something sort of related.
Yeah.
Which is, I'd like, a semi-classical description of your operator.
Uh-huh.
Now, if your caveman was doing a path integral over gravity, because
Yes.
smart caveman,
Of course.
He used the fact that all gravity fluctuations are diffeomorphisms, were large diffeomorphisms.
Uh-huh.
So there's a crude way to do it by just doing the path integral array about.
Yeah.
So there's a smarter way to do it, which is just do the path integral over the physical case.
Uh-huh.
You use the fact.
Uh-huh.
So I would have thought that there would be a way that goes this way. That is, for any one choice of large diffeomorphisms, you have a classical.
Classical solution, yeah.
And then you integrate that over all diffeomorphisms because
Uh-huh.
diffeomorphism actions are different.
Uh-huh.
Is that right?
That sounds completely reasonable. I mean, I don't know how to, we haven't done that calculation, but that sounds reasonable. So, okay, so this is the kinematics, focusing on the ZZ bar plane.
I'm just saying, sorry, just so you must go on, but the physical thing would have been when you sum over all large diffeomorphisms, if you're computing, say, a 2-point function in the bulk, you keep the physical distance between the 2 points fixed, as defined in some way. Take some geodesic between them, this, that, and the other.
No, that's not what.
That's not what I'm doing.
That's
Yeah.
what he's doing. But
Yeah.
I'm just saying, I mean, that would be the proper gauge invariant quantity that you might.
I mean, this is a gauge invariant quantity. That could be a different gauge invariant quantity, but
So this is something I agree with you.
Yeah.
It's not the sort of natural thing I would have done
He's fixing all the small diffeomorphisms by his personalization, and therefore only large diffeomorphisms are there, and they are actually passing through variables, and it's not physical.
It's physical, but if you
Yes,
ask me in the end, what did he
it's-
compute? It's not.
Yeah, I think something saying if you did it not in Graham performance coordinates but in some other gauge, you
Yeah.
get a completely different outcome.
That's absolutely
outside,
true. That's
It's in that sense not a gauge invariant object.
That's
you know.
absolutely 100% true, but that is just what you have to do when you're trying to define a local observable in quantum gravity. I mean, the lore is these observables don't exist. I mean, we're trying to define them anyway, and so they depend on our gauge choice. I mean, that's just 100% true. But if you make a different gauge choice, then I can say, well, that's not the gauge choice I like, and yeah. So there will be some other choice for what phi is in a different gauge, and I'm not telling you what the answer is in that case. An interesting thing that I don't know the answer to is maybe there's some way of taking these correlators and doing something very, very nice. And once you know the correlators in this gauge, maybe you can transform them to another gauge in some natural, nice way. I don't know how to do that. I think that's an open, interesting question. But we're just going to work with this. So
Meant that phi is scaled by ln with m greater than 2 would be
that is what's fixing the gauge, yeah.
for
Yeah.
other gauge, what sort of
You would get something else. So I don't know what you would get. But if it was, yeah, I mean, if it was a small modification, presumably it would be a small deviation from that. But I mean, if it was a very qualitatively different kind of gauge choice, then I don't know. Okay. So there are many different limits we can take to compute this two-point function. So one of them is the semi-classical limit of large central charge with h over c fixed. So this is exactly the thing that I think you should be able to compute kind of along the lines of what Shiraz was mentioning. I mean, probably we have not done this calculation. It's interesting to do. You could just compute the classical solution to gravity given some heavy field and its two-point function, compute the full back-reacted two-point function, and it should agree with this. So anyway, we did this calculation in a different way using sort of fancy Virasoro techniques. And just as an example, this is the leading result at small h over c. It takes this form. So this part, in case you see it in the future, this is just the free propagator for a two-point function in future global ADS. And then this is some semi-classical correction in the limit of large central charge. This is just a sample. There's another interesting limit that you can take, which is very useful for a technical reason and also will show our first pathology. Now, you would probably expect this to be pathological, but you can just do it. What happens if you take the two-point function of phi and you take the limit that h goes to infinity? The leading result is at very, very large h. That corresponds to fixing the central charge and studying a quote-unquote bulk field with infinite mass. So you should not expect this to make very much sense, but there's actually just an answer, which is some complicated function, where there's this q variable that's this other function in terms of elliptic functions, et cetera. The details of this formula aren't important, but what is important are two things. Yeah.
So there you've taken h to go to infinity and also taken c to go.
No, c is finite, so c is fixed. So c is a number that just appears here. So we were able to determine with various finagling the exact. So the answer to phi at large h is this function plus 1 over h. And c can be anything. So this result is interesting for two reasons. One is very technical. It's useful as a seed for something called the homological recursion relations that we're going to use later. But the physical fact about this that's interesting is that the formula that I wrote on the last slide, if you parse it and digest it, has a branch cut starting at rho equals this value, which corresponds to a physical separation in terms of geodesic distance in empty ADS of this value. So what that means is that, surprisingly, I mean, you might have expected this formula would just be something that was just complete nonsense. It's not literally complete nonsense. But what it is at very, very small rho corresponding to very, very large geodesic separation, there's nothing obviously wrong with this formula. It's just some function. But at a separation between these two fields of order, I mean, slightly larger than the ADS length. This is just a space-like separation. This develops a branch cut. I mean, the fact that it develops a branch cut also means it has some singularity. And so what you would say is that bulk locality has just completely broken down at the ADS scale. So not surprisingly, a trans-Planckian field at finite central charge does not have healthy correlators when you try to bring the two phi's together at smaller than this separation. So that's our first indication. It's very sharp. We have an analytic formula, and that's just the answer. So now we're going to study the image.
Sorry, what was the signal of bulk locality?
So at space-like separation, this two-point function develops a singularity, and then at any shorter distances, it has a branch cut, which means it picks up an imaginary piece. So I think the fact that it has an imaginary piece is bad. I mean, I think it shouldn't be allowed, but I mean, the fact it also has some sort of singularity at finite separation in order to have a branch cut.
And unitarity here means in the sense of...
All I mean by this is that it picks up an imaginary piece, so I don't think it should have an imaginary piece. To all orders in perturbation theory, it won't have an imaginary piece. Okay. Yeah.
So this just follows from the formula for phi in terms of...
Yeah, I mean, it just follows from the formula. I mean, in order to determine this, so I mean, I'm not telling you anything about all of the technical stuff that we use to compute this. There's this thing called the Menadri method that you can use to compute conformal blocks. We generalized it to compute this thing.
But the idea is to go to the boundary, expand it into the boundary O's, and then take the point function of boundary O's.
Well, I would say the way that we're doing it formally is I would say, I mean, you could do it that way. So, I mean, you could compute to any order sort of that way. But to get these kinds of formulas, what we're really doing is we're just doing the two phi's as CFT operators. And then we're making some statement about, I mean, we're viewing sort of phi is here and phi is there. And then you can sort of sum over what all of these intermediate states. And it turns out that, that there are recursion relations for that, et cetera. But
you're not coming over the internal states, right? Because this is the proto field.
well, I mean, there's some internal state. I mean, when you compute the phi two-point function, it's the OO two-point function dressed by lots and lots of Virasoro operators, which means that you take lots of derivatives of it in various ways and sort of put them together. So that's all I mean.
And how trustworthy would the gauge-dependent answer be at a non-gauge?
I mean, a point that I should emphasize is there is no bulk observable that isn't gauge-dependent.
The distance has to be set. Keep the distance fixed.
Well, how do I define the distance? I mean, the distance is some semi-classical idea. I mean, what do you mean?
Well, you could say I'm going to measure geodesics for each metric, and then I'm going to sum over the metrics.
So he wants to do it on the field plate, the boundary.
But
I'm just saying conceptually, if you're summing over large diffeomorphisms, you could think of defining.
But you're going to sum over spacetimes where there's some black hole in between and there's no geodesic. I mean, how do you know there's the spacetime doesn't have to be geodesically complete in between the operators?
So
I
there's
mean,
more than one geodesic that you keep the points outside, and there's more than one geodesic,
Uh-huh.
and you say, okay, I take the shortest of them, or I shoot null rays I use the boundary of ADS, I shoot null rays, I use proper affine times from there. There are various ways you can think of trying to.
you can. I don't know how to compute the answer. I have no idea how to compute the answer. So here, I mean, I think the Pfefferman-Graham gauge is a pretty natural thing to do, and we know how to compute the answer there.
doing something drastic, right? Like, well, locality is broken down.
But I don't think. Well, okay. I don't think of that as drastic. I thought that was the expectation.
So far only for very large.
Yeah. So far. So we're going to see it break down. So here's an expectation that you might have had. Bulk locality should break down at the Planck scale.
Oh, wait, in higher dimension, I would have said it breaks down on the scale of the size of the black holes that you create. Very large H would be creating very large black holes in the basket.
Exactly.
Case 3, I have no intuition.
So I mean, I think that this is. I mean, I would have guessed that intuition as well. That would have told you that it should break down when h goes to infinity at distance of infinity. And that's not, I mean, this is in some sense a more conservative answer than that because it's saying that it only breaks, we only are saying it's guaranteed to break down at this scale. I had that expectation too. I was hoping to see that it was the Schwarzschild radius, and that's
All these
not.
things make sense in ADS3, right? Schwarzschild radius.
Short, yeah. BTZ black holes have Schwarzschild radii.
I have no intuition to this story.
Yeah. So I mean, you might have, yeah. That was my hope. That was not the answer. Good. So now let's talk about light fields, and where we can sensibly talk about doing, say, 1/c perturbation theory. Now I'm going to tell you something surprising. I found very surprising. That has nothing to do with anything fancy. It's just a property of doing the one loop computation that's pictured there. And as far as I know, no one had ever done this one loop computation before. And bulk one loop calculation. So we did the bulk one loop calculation exactly. This is the short distance expansion of this. So remember, sigma is the separation between x1 and x2.
And I'm very sorry, this is in which bulk theory now?
This is just ADS3 pure gravity coupled to a scalar field. So it's a free scalar field. Yeah. So this is the diagram that we're literally talking about computing. There's some one loop propagator from the graviton. If you study this 2-point function in just this
In this gauge?
in this gauge. So this is a gauge dependent statement, and this is in this gauge. The 2-point function of phi at short distances, so expanding at small sigma, takes this form. So 1/sigma is the way that the free field 2-point function behaves. This is the correction, and you find something very surprising, at least to me, which is that there's a new length scale emerging, which is some intermediate scale between the Planck scale and the ADS scale. So capital R here is the ADS scale. So I mean, if you just look at this term, you see that there's a sigma to the fourth, and then there's this thing that has dimensions of length to the fourth in the numerator. So this one loop correction is becoming big at this new intermediate scale. What you would have expected, what I would have expected, is it should get big at the Planck scale.
You're saying there's in the order of infinity limit, there's an IR there.
Exactly. So we're in ADS3, so there are no IR divergences. But in the flat space limit, if you send R ADS to infinity, there would be some IR divergence. But I mean, if we're really in ADS3, we don't have to care. But this is weird. I mean, this is a UV IR mixing. I mean, there's this mixed scale between a UV scale and I think of the ADS scale as an IR scale. And this is just a property of this one loop diagram. So I mean, you might try to find some way of computing this or some new gauge in which this doesn't happen.
Is there somehow the statement that everything non-trivial in gravity is happening at the time?
I mean, maybe, but I don't know how to make that useful.
Or I was saying in 3D also that the effects don't die out at very large.
That's for sure. I mean, it's certainly true that like if you have two particles orbiting each other, that like they affect each other at arbitrarily large distances. So I mean, it's not surprising there's an IR divergence, but I mean it leads to this particular scale.
But it's sort of important to know that when this was Sandeep said, I want to know whether it's the propagating degrees freedom of gravity or the Coulomb law.
So I see.
I mean, there aren't any propagating degrees.
The boundary gravity. The boundary gravity.
That's all there is in this computation, right? So.
No, but there's the Coulomb field. The propagating modes of the graviton, there's the Coulomb field.
Okay, good.
And these are totally different physically. And which of these is giving?
I mean, I can tell you at a very, very specifically at kind of a technical level what's going on.
You must, but let me just say to Shiraz, it's not clear to me in ADS3 that the Coulomb effect is any different from the boundary gravity.
Okay, this may be. I have no idea.
Yeah.
Because it's a large isomorphism.
Yeah.
No, but there are no degrees, there are no states associated.
So let me just tell. So
That's Hilbert space associated. There's no Hilbert space associated. Are you saying you can't have one without the other? Maybe.
So, I mean, I'm just going to tell you just a technical statement, which is that.
And you have notebooks for each one of them. It does not require a transverse photon still, but you have to be emanating from fluctuating charges.
I'm sorry to interrupt, but just so if we just stay in the vacuum of the data solar module, there are still Coulomb.
Just ADS.
No, you put some. You've got the 2.5. You've got
Well, if you could, well, I mean, yeah, I mean, these are sort of states being, in some sense, formally exchanged between the two scalars. What I was going to say technically is that this all comes from the fact that the graviton propagator takes this form.
How can they not be back? Sorry.
This phi, do you have a back reaction here in this particular calculation?
Well, this is, I'm imagining phi has a very small mass, and I'm doing perturbation theory in G Newton, and this is a one loop diagram.
It's a graviton that's
It-
propagating the boundary. Right?
There's a scalar line and a graviton line, yeah. So this is, yeah,
So the graviton is exhausted.
yeah.
There's a bulk.
Bulk scalar field, and then you're looking at the thing where, yeah.
I mean, yeah, the bulk scalar is radiating a graviton and propagating and then reabsorbing that graviton. That's what this is.
You should go with it. What would you call a conical deficit provided?
That's the Coulomb.
Is the Coulomb, right? So if you had a small object, or even a big one, whatever, in ADS3, it would generate the conical deficit, right? And if you sort of had two of them, one around the other, they would see this, right?
So, I mean, I think this is the Coulomb thing, right? I mean, you're exchanging a graviton between two propagating things. I mean, this would be the computation you would have done for Coulomb, right?
Yes.
I mean, this same propagator is what we're using here, except the propagator is wrapping back and doing this. I
And
mean,
the boundary conditions for this propagator, are they allowing these large diffeomorphisms?
I mean, that's why I wrote down, this is the exact formula for the propagator in this gauge. So for HZZ at Z1 and HZ,
Can you fix the large diffeomorphism?
yeah, I mean, I would have said so. I mean, this is the propagator in our gauge after gauge fixing. So note that it doesn't depend on y at all. HZZ, these two HZZs should depend on y1 and y2. Propagator has no dependence on y1 and y2. It only depends on z1 minus. So this is exactly the two-point function of a boundary stress tensor at the point that you project onto the boundary. That's in this gauge what the propagator is. And so the fact that this has a fourth power singularity as z1 approaches z2 is effectively, I mean, it's not literally why this is 4. There's some algebra, but that's why this is more singular than you would have expected. So I mean, but that's just a technical
Maybe
statement.
just one more small thing.
Yeah.
Which is that I've done this calculation once, that you take 3D gravity in flat space, and interestingly, it has a sort of graviton in it, and then you can do the scattering, Coulomb scattering.
Oh, okay.
The graviton is not propagated.
Well, when you linearize, you'll get
When you gauge
that
fix,
couples-
yeah.
Yeah, after gauge fixing, and you do the linearization, you get something that couples to P mu nu,
Yes.
and you can do the three-level exchange,
Yes.
and you get you see the deficit angle.
Yes.
And I think
I
you
see.
would have called that a Coulomb.
I would have thought that.
Yeah.
There's
Yes, I
nothing
would have.
funny happening.
And there's nothing funny you can do in it. So I was
Yeah, yeah.
thinking,
Yes, yeah.
Yeah.
Anyway, please.
Yeah, I mean, that's very interesting that we should talk later if you have time, because I'm curious if you can do that calculation of this loop in flat space and see what happens. Okay,
It's been a while, but I can.
I see. Okay, great. That would be nice to hear about. So that was just straight one loop perturbation theory. Now we're going to use these fancy Zamolodchikov recursion relation techniques. So it turns out that you can actually compute the propagator to all orders in the short distance limit analytically. So this is not the exact result, but the all orders in perturbation theory result. To leading order as sigma goes to 0, to all orders in perturbation theory, you get this very simple, very simple function. This is an asymptotic series, as you might expect for perturbation theory and a field theory. You can Borel resum it. There's a pole on the real axis, which I guess normally people would say that means that it's the Borel resummation is ambiguous. And generically, the Borel resummation gives you an imaginary piece. So that's what you can just see this analytically at all orders in perturbation theory. But here you see the sigma to the fourth. I mean, this strange intermediate scale is showing up, and it's going to show up everywhere. So you can use the Zamolodchikov recursion relations to compute things exactly. And so a very simple thing you can do is, what does the Zamolodchikov recursion relation actually give you? What it gives you is the exact coefficients in an expansion in small rho. Remember, small rho is long distances, because rho is e to the minus 2 sigma. Now, if you have an expansion to very, very high order in this rho variable, you can ask, what is the radius of convergence of that expansion in rho? that will tell you about, very likely, where the function develops a singularity in rho, which in turn tells you where it develops a singularity in geodesic separation. So this plot, which, I mean, there's no reason to sort of obsess over it, but this plot is a plot of the ratio of the coefficients of rho to the n in the rho expansion, which means that what you see here, at least so this is for different values of c with the same value of the bulk mass, so you're just sort of taking the large C limit. What you see is that the ratios of coefficients are stabilizing to some constant, which means that the coefficients are growing exponentially, which means that the radius of convergence is smaller than 1, and as can be determined by this. So if you use that information to read out what is the radius of convergence in sigma star, so the radius of convergence here is sigma star, as a function of central charge, you can make the plot previously for 30 or 40 different values of the central charge, and you can ask what is this radius of convergence converted to geodesic separation, and this is the answer. So these data points are for different values of c from 1 to 100,000. At very small values of c, what you find is that the radius of convergence is of order the ADS scale. So what that says is that if you try to create a bulk field in a theory with a small central charge, then locality breaks down at the ADS scale. And in fact, it didn't have to be this way, but at small central charge with fixed bulk mass, you interpolate to the same scale of breakdown as we found in the very, very large H limit with fixed central charge. So in other words, large H and small c are sort of seem to be the same regime. So this line, this red line, is like what the value was that we found from large H. So we have breakdown at the ADS scale. But if you make the central charge large, then of course you'd expect that there should be a big hierarchy between M Planck and the ADS scale, and so you'd expect locality to break down only at some much more microscopic scale. And that's what we're finding here. So as you see, this is decreasing. This is on a log scale for both. This is decreasing as a function of the central charge. So in other words, locality is good to shorter and shorter distances as you increase c. And you can fit this to this power law behavior. So remember, we had this expectation that it should be c to the minus 1/4, because there was this scale that was g Newton to the 1/4, so that's c to the minus 1/4. And you can fit this just numerical data to a power law, and it's reasonably quite close to c to the minus 1/4. It's minus 0.27.
You think it asymptotes to c to the power minus 1?
That would be my guess. I mean, I don't know for sure, but I mean, this is using a lot of numerical data.
I'm sorry, can you just go back so I can see how rho was defined? I got it.
Okay, maybe I'll just write it on the board again. So
You were computing the 2-point function.
so sigma is the geodesic distance
Okay, between the 2 points.
between the 2 points in empty ADS, and rho is e to the minus 2 sigma. So small rho is large distance. Good. So
Just to make emphasize, it's a 2-point function you're computing.
yes. So yeah. So this is just the in the 2-point function in the vacuum, sigma distance in the vacuum between x and 1 and x2. Good. So what we see is that it seems like things break down at this scale. I didn't expect this intermediate scale to appear. I mean, I would have been very, very, very happy if this had just been g Newton, then it would have been the Planck scale. But it's this weird intermediate scale, and I don't really know what that means. One possibly interesting coincidence, maybe you know something, you have something to say about this, is that if you take a compactification of string theory, you never have ADS3 by itself. You always have ADS3 cross other stuff. And you can ask, what is the string scale? And I am not an expert. I might just be wrong about this. But as far as I know, if you have a controlled string compactification, it always happens to turn out to be the case that the string scale is always bigger than, or of order, this scale. Now, this may be a coincidence, or it may be some deep fact that somehow string theory knows that it should do something. I mean, I just don't know. There are M theory examples where there just isn't a string scale, and then I don't have anything to say. But that's anyway. That's all I really have to say about what the scale might mean. There's also semi-classical data, so you can study the case where you let H change and let C change. So this is some interesting thing. If you take as a function of H over C, with different values of C, you can see what this scale is. And there's a semi-classical expectation just from using semi-classical techniques to get the answer. And at large C and fixed H over C, these seem to be matching. I mean, we need to continue this curve, but anyway. And then for C small, you can see that the scale at which the breakdown happens is always bigger, and it approaches this value. So I mean, once again, at small c, physics breaks down at the ADS scale, but then if c is large, it doesn't have to. Okay, so basically that's it. The summary is that it's possible to define what we should mean by an exact local bulk observable in this particular gauge. It totally depends on that gauge choice. If you can do this in a different gauge, or if you know how to adapt this to different gauges, I think that would be very, very, very interesting, because we would like to know what happens in other gauges. But I told you what happens in sort of Pfefferman-Graham. And although we defined this thing as some sort of precise infinite sum of local operators, which is really non-local, so it had some kind of precise definition, if you compute the correlators of this object, then they violate locality and in some sense unitarity, because they pick up an imaginary piece at short distances. And this is a consequence of non-perturbative effects. Maybe I didn't emphasize that, but if you just work to finite order in 1 over C perturbation theory, everything's real, and the only singularities occur at coincident points when the two bulk operators come together. But in the infinite sum, there's this new non-perturbative scale, and locality breaks down. And so there's obviously lots of other stuff you can try to do. One question that this raises that really I hadn't been thinking about very much before is we have a unitary CFT, and we try to define a bulk observable, and what we find is bulk locality breaks down, but also in accompanying this breakdown of bulk locality, there's some sort of violation of what you might call bulk unitarity due to these non-perturbative effects. So I mean, I've always imagined that since the CFT is unitary, the bulk theory has to look unitary, and therefore, for example, there's this information paradox. That then tells you something about what the information paradox should look like. If it's really possible that when you try to define bulk observables, you get small violations of unitarity, but that somehow go away when you define true CFT observables, then that might mean that there's some intermediate regime where the information paradox can be resolved. I hadn't really thought about that much before doing these calculations, but I don't know. Nothing yet has anything to do with black holes, and there's no direct signature of black hole physics in any of this. But what the next thing that we want to do, naturally, part 2, is compute, say, phi O or phi in the background of, say, some heavy operator. And that's technically significantly more complicated, but I don't think it's sort of necessarily insurmountable as a thing to try to do. That will depend on lots more details. So here phi, the 2-point function of phi really doesn't sort of depend on any conformal data except the dimension of phi. But if you compute phi in, say, a heavy background, then that will depend on all sorts of conformal block decompositions of all kinds of things, which depends on CFT data. And there's some question of which CFT data will matter, et cetera. I don't know. There are other questions like, what does this mean for other people's work on sort of bulk locality? I mean, there's been a lot of discussion of quantum error correction, and I really don't understand a lot of things about that, but you would expect that there should be some connection. Yeah, and then I have no idea how to do this, of course, in higher dimensions. It would be very interesting, but possibly doable to understand what this means in other gauges of ADS3. If you believe in DSCFT, then you could try to ask what this means in de Sitter. That's it.
Thanks so much for a great set of exhausting lectures.
You can all go to sleep, yeah.
No, I mean exhausting for you. Really great.
Thanks. Okay.
So this graviton propagator, how do I understand that? Is it like some version of the Schwarzian propagator, or what I mean to say?
Yeah.
Is that so if I think of sort of reducing the quantum gravity path integral in areas 3
Mm-hmm.
To some path integral over large differentials. They will have some kind of action. Let us say. It's so I know what the ADS2 version of that is. That
Mhm.
is the Schwarzian.
Mm-hmm.
And then indeed it so happens that if you compute some phi stuff,
Yeah.
then the Green's function acts for any fixed large differomorphism.
Uh-huh.
Okay, the phi 2-point function is something that depends on those differomorphisms.
Uh-huh.
Then you are integrating over them later on.
Yeah.
So then what happens is that something like the differomorphism degree of freedom 2-point function of those, they come into the picture,
Mhm.
and there's some action has been computed, that's the Schwarzian, and you
Mhm.
just plug it in, and you get the phi
Mhm.
done that way. So phi
Okay.
will have some usual thing,
Mhm.
okay, plus the contribution coming from what you might call here, graviton propagator.
Mhm.
And indeed, it so happens that, as expected, there's a 1 over square, there's a 1 over n with each of these vertices. There's a phi epsilon
Yeah.
thing. So, is that the kind of this graviton propagator which you have here? Is it that?
I would like to know. I don't know. What I'm imagining for this calculation, maybe I should say what do I mean by, I really mean sort of this diagram where I imagine I fix the gauge for gravity and then I'm left with some residual, I don't have any locally propagating degrees of freedom, but I have some sort of HZZ and HZ bar, Z bar. And they have some 2-point function in the bulk. I think in this gauge, this is the 2-point function that I find. And then if I have a free scalar field, that couples to the metric, and if I expand to linear order in HZZ as a fluctuation around pure ADS, then I would have thought that I have vertices like these and maybe other vertices as well. And then I'm just sort of doing this naive thing. Now, I don't know whether that's equivalent to what you're saying. I'm not sure. It's possible there's some argument that this isn't the right thing that you should do. But
Maybe I can ask,
yeah.
how did you get this HCZ right?
Good. So I fixed. So I think that's pretty simple. So I fixed my. I fixed the gauge to take this form. So I think it's natural, and I believe it's correct that I can view empty ADS, but sort of quantum mechanically, I can view this is a formula for the quantum gravitational field, where this is the pure ADS part, and T bar and TT bar are sort of the linearized quantum fluctuations. Like at large C, I can just view these as small perturbations. And if I view it that way, then I can compute the propagator of HZZ with HZZ at a different point, and it's literally the 2-point function of T, and that's how I got this propagator. So it's because I fixed this in a different gauge, it will take a different form, but I think that's.
So there is a story about the 2-point function of T which comes from. What I mean is that there is also phi. There's a matter field.
There's a matter field around, yes.
So there
But I'm expanding around a limit that there's no back reaction. So to 0th order at infinite central charge, there is a phi, but it has no effect on the geometry at all. And then what I thought is that by doing perturbation theory, I'm going to expand in sort of these interactions that involve propagators from T around that. That's the philosophy. And one thing I know very well is that applying this philosophy where I imagine a propagator from phi to O instead of phi to phi, and say I use the stuff on the slide, that gives me very nice formulas for all these kinds of correlates.
Euclidean space and Minkowski.
Everything about this is in Euclidean space.
This propagator is only for
No, I mean, this should work in any vacuum ADS metric, so T and T bar can get vacuum X. So for example, if I insert a very heavy operator at 0 at infinity or something, then T gets a vacuum expectation value, which is like H heavy over Z squared, and then this metric is the BTZ black hole metric in some gauge, and then I get the phi correlators in the BTZ black hole background. We didn't do the calculation of the phi correlators in a BTZ black hole background, but that's the calculation we would do to do that.
You want a one-point function of phi with the real black hole background.
So that is a thing you could do. You could compute phi with O heavy, and then if the O that phi comes from has a 3-point function with O heavy, then you would get some formula. That should be an easier computation.
But will you see some feature as the approach horizon?
I don't know. I mean, that's a good question. In a semi-classical limit, you get whatever the sort of semi-classical answer should be, assuming the 3-point function exists. But I don't know what you would get quantum mechanically, and it's an interesting thing to try to compute.
But carrying on along those lines, the kind of question you'd like to ask is that if you got into a spaceship and you went into the horizon, do you get torn up?
Yes.
Something like that.
Yes.
Or if you send a wave packet from the boundary, does it get torn up?
Yeah, exactly.
Okay, so you can send a wave packet from the boundary by turning on an operator at the boundary.
Yep.
That near the boundary reliably creates some wave packet which you can characterize, and you
Yeah.
want to know what happens to it in the future.
Yep.
Now, how do you translate that physical question into a statement about your operator? Or correlative of your
I mean, I think the naive translation is that you analytically continue to Lorentzian signature, and then you ask what, say, the 2-point function at time-like separation of phi is, or what the 2-point function of phi with a boundary operator is at some time-like separation, and you study what happens to that in some background.
And there's so much ambiguity in the definition of this phi that could be that this guy is singular but some other gauge is not. I mean, it would be nice to have it clearly physical, like answering a clearly physical question.
To me, a better way of saying that is, it would be nice if we could compute that in any gauge, and we could see whether it changes a lot in a way that makes the answer very, very different in different gauges. I mean, I don't think this is an unphysical question, it's just the question you get in this gauge. I mean,
No, but there is a physical question. That is, if you go into the rocket ship, then you get torn up.
I mean, that's intuitively physical because we live in a gravitational space-time, but I don't understand why that's, so, I mean, the way that we would model that using the physics we know is we would study the standard model in a black hole background, and then we would ask for correlators in some gauge in gravity, and we're used to thinking that it doesn't really matter that much what gauge we choose, and we could, at least at the semi-classical level, and we can just compute it and we get some answer. I don't see why this is giving you some exact formula that in perturbation theory I think agrees with that intuition. I mean, unless you think for some reason that Pfefferman-Graham is a very unnatural gauge.
No, I have no opinion on that. I'm
Yeah,
just
yeah,
saying that there is a question which presumably has an answer, which is, do you get torn up or not? That's not an ambiguous question.
I mean, I guess I thought that the lore was that could be it. I mean, we don't know. I didn't think anyone knows how to ask that question in non-perturbative gravity.
This may be.
Okay.
But presumably there's an answer, right? Which you'd find out if you went into the black
Yeah. I guess I would have said that this is the best way this is sort of the best way I have at trying to answer that question exactly in gravity.
Yeah.
A 3-point function cannot solve this question of phi and O heavy.
I don't think so. I mean, I think that's telling you something like what's the classical Desmond phi due to the black hole. And I think what you want to do is you want to create like a spaceship. I mean, if phi was an operator that creates spaceships, then you'd want to create a spaceship and then measure the spaceship.
Spaceship could be a wave packet. Wave packet is fine.
Yeah.
So you torn up, that's like spaceship. Right?
Yeah,
That's
yeah.
an easy thing to do at the boundary.
Yeah.
What's difficult is to understand what the guy sees in the boundary.
Yeah.
I don't know how to do that.
But, I mean,
If the distance at which we drawn up is given very.
I guess what I would say, Shiraz, is that I think we all know how to do this in the bulk if we just use bulk field theory. And I mean, I think that if I give you something that agrees with bulk field theory to all orders, and then is an exactly defined thing, you can ask, is the exact part of it that differs from bulk perturbation theory ambiguous? And it will be with respect to gauge transformations, but I mean, at least that's being made precise. And then, I mean, this is one answer to the question.
I agree there's great value to what you do. I'm not disputing that.
Sure.
What I'm saying is this, that if you you make some definition, you get the answer that everything's bad,
Yes.
then you don't know what I'm saying. If you make a definition and you find everything's
Mm-hmm.
Okay, so as per your choice of gauge and so on, you can say which operators are space-like separated or not.
Yeah.
In that sense.
Yeah.
You know. Or let's say you compute the commutator and you take some large C limit or something, you can try to roughly see what operators are space-like separated. So could we say which operators would be such that one point is beyond the horizon and the other is not? Just as a start, as seen in the.
You mean can you see sort of the causal structure of the black hole background?
Yeah,
No, I
yeah.
think this is a good question. I mean, you should be able to see the causal structure. For example, it just when the background changes because you have some sourcing just at the semi-classical level, you really should be able to see that by some yeah. So I think that's also an interesting.
That was the first thing I thought maybe was,
Yeah.
I mean, I'm sure I think of this, but to Shiraz's question,
Yeah.
if we can start getting a handle on the causal structure, then we can start asking, hopefully, what happens if one of the points goes beyond the horizon.
Yeah.
And so on. Then, as you say, we have to make it more precise to see what the
Yeah.
And you know, suppose you get the answer that you're torn up. There could be another definition which you're not.
Yes.
That would be the good definition.
Yeah, so I mean, I think to be more specific with this, I mean, well, you would hope that's the good definition if you're going to jump in. But, I mean,
Okay, I thought what you were going to say is torn up means at some point perturbation theory gets terribly bad in computing the answers to those questions. You know.
so I think there's a very specific
That's
question.
bound to be what will happen, right?
Well, hey, you can get torn up by tidal. I mean, suppose there's a crazy firewall, you can get torn up within the regime of perturbation.
So you get the firewall.
Okay.
Suppose it's happening at
But-
the same time.
No, not that, but the horizon.
Yeah, I think
we're talking.
Yeah.
Yeah, I think we're interested. So I think Shiraz, I think
I misunderstood.
yeah. So I think there's a very specific thing, which is we know that in Schwarzschild coordinates, which is I think what Pfefferman and Graham also sort of looks like, it looks like the horizon is some special place that at least looks thermal and weird. We also know that there's Kruskal coordinates where the horizon looks very smooth, and it makes it obvious the horizon in GR nothing special should happen. So I think a very well-defined question you can ask is, say we try to do this procedure, but we try to make Kruskal coordinates the natural coordinates.
Use
Now-
Eddington Finkelstein to in my advice.
Okay, Eddington Finkelstein and going.
For an eternal trust, that is good enough.
So Kruskal coordinates by definition are the coordinates that are useless for this guy.
Not for an eternal.
That sounds ambiguous. So you try to do Eddington Finkelstein coordinates. So
Any sane observer will use Kruskal for an eternal. Sane observer.
So so if you could find some Eddington Finkelstein coordinates that naturally work for sort of a black hole of any mass, like you some parameterized version, you could try to do exactly this kind of setup, but in that maybe that's a different gauge, and maybe you get a very different answer, and maybe that would tell you something very interesting. And I mean, I think that is a very interesting thing to do. But right.
I think we give it a big round of applause.